So what I'm going to do today is an application of the theory that we learned so far. So you are familiar with this phenomenon. It's the emission of electrons from a metal when heated to a sufficiently high temperatures. This is known as thermionic emission, right? And you may have used electron guns while doing some experiments in the UG lab. For instance, there's an experiment where you verify E by M ratio, right? So there's an electron gun that emits electrons, and these electrons are moving around a circular path in the presence of a uniform magnetic field. You may have done that experiment in your second year. Okay, so this is basically what we are going to study today, thermionic emission, which refers to the emission of electrons from a hot metal surface. Okay, emission of electrons from metal when heated to sufficiently high temperatures. High temperatures. Now this high can vary from metal to metal, and it's typically this temperature which I'm calling high. This is of the order of few hundreds of Kelvin, so 800 to 1000 K. That's the order of magnitude. Okay. Now, maybe in the 50s of the decade of 50s in the previous century, there were a lot of experiments that were done using this kind of a tube. This is known as vacuum tube or electron tube. Okay, so this is a glass tube. And the diameter of this tube can be around 15 millimeters, 3/4 of an inch kind of, and in terms of length it can be about 50 mm long. So this is a vacuum tube. Or some people also call it an electron tube. Okay. And the other very popular name is vacuum diode that you may have heard about. So before the solid state diodes were discovered, the radios and all televisions used to employ these kind of diodes. So what is it actually? I haven't really explained anything about this. So it's very simple. There is a cathode, which is a metallic plate, and then underneath this there is a heater. Okay, so you pass, and inside this tube there is a high vacuum. So that's why it's called vacuum tube. And then there is an anode. So between anode and cathode, you connect a high positive voltage, okay, and this is variable, you can vary it. So let's call it V. So this is V anode, and you pass a certain, you apply a voltage, pass a current through this. This is the heater. So this is VH, the heater current. So when you heat this up, heat the metal up, then the electrons are emitted, and these electrons are then, they move towards the anode if a positive voltage is applied. So you can plot the IV characteristics. Of such a tube, and the IV characteristics, they look typically like this. This is saturation, and if this experiment is, let's say, performed at some temperature T2, okay, this is the temperature of the cathode, because you're heating the cathode, so the electrons are emitted. And if you lower the temperature or increase the temperature, this current is going to change. So basically what you see here are two regimes. A regime where the current is increasing as you're increasing the anode voltage, and the second regime where the current is not increasing, it is saturated, right? So this is the saturation region, where the current is limited by the temperature. So if you change the temperature, that's what I was showing you. So if you change the temperature to T1, where T1 is less than T2 or T2 is greater than T1, then the saturation current will be smaller, okay? So this regime, in this regime and in this regime, there is a difference. In this regime, what limits the current is the temperature, right? So this regime is called temperature limited regime. And this regime is the region where the current is increasing as you are increasing the anode voltage. And the reason is that when you heat it up, the electrons are emitted from the surface of the metal, okay, and these electrons, they start accumulating. Suppose you are not applying any anode voltage, the electrons will start accumulating above the surface of the metal, okay. This is known as space charge. The space charge will build up. So in this regime, which is called the space charge, this is known as space charge limited regime. In this regime, the emission rate is higher than the rate at which the anode is, sucking the electrons, absorbing the electrons. All right, so this is the space charge limited region. So in this region, the emission rate is more than the rate at which you are pulling the electrons towards the anode, because the anode voltage is not high enough. And this is the region where the rate of emission is same as the rate at which the anode is pulling the electrons towards itself, because the anode voltage is high enough. However, you are increasing the anode voltage, but the current is not increasing. Why is that the case? Because the current is determined by the temperature of the metal. The higher the temperature, the more the electrons will come out, right? And the higher will be the saturation current, right? Does it make sense to you, right? So if your temperature is too low, I mean, let's say at room temperature, no electrons are coming out. You will not have any IV characteristics. So you need to heat the metal surface, and you need to heat it to temperatures as high as 800 to 1000 degrees. All right. It depends on the metal that you're choosing. For instance, for tungsten, you need a temperature of about 1000 Kelvin. 1000 degrees centigrade or Kelvin is the same difference of 200 odd degrees. So that's the kind of temperatures you need. But then you can have some very advanced cathodes where you can achieve the same current density by having a smaller temperatures, right? So what decides that? That is determined by the work function of the metal, right? So there are two regimes. This is the space charge is what limits the current here, and temperature is what limits the current here. And in this regime, what is important is the work function of the metal. right? So, for instance, if you choose a material which has a lower work function, then you would get a higher current density at the same temperature, right, without even going to higher temperatures. So, that is the whole point. And you may have seen that there is a slight negative voltage which is required in order to reduce the current to 0. That is because the electrons that are coming out, they have some thermal energy. So, they can overcome even a small negative potential to reach the anode. All right. So, that is why you can have a little bit of a negative tail. Okay. This is known as splash current, if you want. So, now what is very interesting is that in this regime, the current density is given. So, the current density J, and let us say this direction is, let's call this direction as x-axis. Typically we call it z-axis. Let's call it x-axis because that's what is written in my notes. So, let us call it x-axis. So, this is your anode, which is red hot, and here is the cathode above it, which is at a high positive voltage, attracting electrons towards itself. Okay. Yeah, so the current density is given by a relation which is J equals A T square exponential minus phi by kT. This is how the current density, it is not the current, it is the current density. The units are ampere per meter square, right. So, the current density, and the current you can get by multiplying with the area. So, the current density is given by this relation. So, it is certainly governed by the temperature. The higher the temperature, the higher the current density, right. And it is also governed by the work function. In fact, it goes exponentially with the work function, right. So, if you change let us say tungsten with another material which has a lower work function, we will get a huge enhancement in the current density at the same temperature, right. And what is A here? A is some constant, okay, and it is not some constant actually. It turns out to be a constant which is independent of the metal that you are using. So, it depends on the fundamental constants, right, once again. And this, let me first write down what is A. So, A is E, the charge of electron, times its mass, times square of the Boltzmann constant divided by 2 pi h bar cube. So, you can see that it depends on fundamental constant, does not depend on materials parameters, right, and this value will come out to be around 120. If you plug in all the numbers over here, this will be 120 ampere centimeter squared, inverse centimeter squared, Kelvin, inverse Kelvin squared. This is the value of A. Now, this relation was derived by Richardson, and this is known as, this equation is known as Richardson's Dashman's law or equation. Okay. So, this is your Richardson Dashman's equation, and this equation states that the current density in a vacuum tube or a vacuum diode. Now, you can see why it is called diode. It is called diode because this current flows only when the the anode voltage is positive. If the anode voltage is negative, no matter howsoever high the temperature of the cathode is, there will be no current flow, right. So, in the olden days, these were the kind of diodes that were used. These days, you are used to seeing a diode which is 1/10 of the size of your baby fingernails, right. It is so small, but you can see the size of this diode and you can imagine the size of your radios. So, the radios used to be huge. These days you are carrying a radio in your pocket, in your cell phone, right? But those days the radio used to be of this size. Why? Because diodes and triodes and whatever, they were all made of tubes like these. And there was a huge interest and there was a huge research that went on, in this direction until the transistor was discovered, the solid state devices were discovered, and then that changed, that revolutionized the whole electronics industry, right? So, but why are we interested here in this lecture in this particular device? We are interested because we are intrigued by this law. We want to derive this law. That's the aim of this lecture, right? Based on whatever we have learned so far, okay? And this derivation was actually given by Richardson, and Dashmans probably contributed to it. Not probably, he must have contributed to it, otherwise his name will not be attached to that equation. And they did it in 1928. And very interestingly, Richardson himself did a lot of experiments and then he derived this law, right? So, it is also based on a lot of empirical evidences that he gathered by performing experiments on different metals, right? And this was around the same time when Sommerfeld gave his theory, because the derivation is based on Sommerfeld's idea of the model of the metal. And in 1928, I believe, yes, in 1928, Richardson was awarded the Nobel Prize in Physics for his contribution. So, the exact citation, it reads that for his work on thermionic phenomenon and especially for discovering the law which was named after him, which is this law, all right. And by the way, one thing that we are not discussing here, but you will definitely come across now that you have come back to ICER, you will do experiments in the lab, you will do Frank-Hertz experiment and other experiments where vacuum tubes are used. All these experiments are in the advanced physics lab course. And you will see that in this law, in this region, which is the space charge limited region, the current is actually proportional to 2/3 of the applied voltage, the anode voltage. Just as here, the current is independent of the anode voltage, no matter howsoever high the anode voltage is, the current is not changing. And this is also a very famous law. This is known as Child-Langmuir law, right? You may have heard this also. So, but in today's lecture, we are going to just focus on the Richardson-Dashmans equation. So, here is the metal surface, which is a certain area and the thickness, and there's a heater underneath it. So, this is the surface, and the x-axis is aligned in this direction, and then you have y and z in the horizontal plane. Okay. Now, first of all, when we did Sommerfeld model, we kind of assumed that the electrons are in a box, right? We choose the shape of the box to be a cube, isn't it? The size of the box to be L cross L cross L. That's what we did. And then these electrons were in a box. We solved the one electron Schrodinger equation, and then we built the ground state using the Pauli's exclusion principle, isn't it so? So, we pretended that the electron can never leave the metal body, which essentially means that the electron lives in a infinitely deep square well potential, right. So, basically our model was something like this, that the potential at the boundary of the metal goes to infinity. So, the electrons, they cannot leave the metal surface. So, here is your 0 of energy, and this is the Fermi energy EF, and then of course, this potential goes to infinity. So, there is no chance for electrons to escape. But in reality, what happens? In reality, what happens is that if you apply sufficiently large energy to the electrons, you can do it by, for instance, increasing the temperature, or you can do it by shining the light of appropriate frequency, or you can also do it by applying a very high electric field, which is known as field emission, right. So, there are various ways you can take electrons out, pull electrons out of the metal. So therefore, this barrier is definitely not infinitely high, right? This barrier has a limit, has a finite height, and this finite height of the barrier is determined by the work function, right? So therefore, the actual situation should look something like this, right? So here is your Fermi energy, EF, and over and above Fermi energy, if you supply this much more energy, which is called phi, the work function, then the electron would certainly be out, because this is your vacuum level. This is your EVAC, if you like. Okay, you can put the 0 of your energy here, or you can put the 0, it doesn't really matter. Typically, people put vacuum energy as 0, right, where the electron is free, and here it is bound, so you put negative. But it doesn't matter, you can choose your 0 anywhere. So that's your potential, right? But in reality, what happens? In reality, what happens is that you have a metal surface. The moment electron comes out, it leaves a positive charge behind, because the metal to begin with is electrically neutral, right? And then it sees a potential, an attraction from the surface, isn't it? So you can model that by the method of images, which you have learned in electrostatics, right? So it would see a positive potential, which is pulling it back, right? So in reality, the potential looks like this. So instead of going up, 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 it has a shape like this. The level is still the same. The vacuum level is still the same. So this is your EVAC once again. And this curvature that you get, I mean, these are matters of details. You don't need it for the derivation. What you need for the derivation is this picture, the second picture. But now I am telling you that what the actual picture is. This is known as the image charge potential. And here is your EF. Now, on top of it, if you apply an electric field, like you do here, apply an electric field. So, outside the metal surface, there is still a force field present, right? So, if there is an electric field which is present outside the metal surface, then this potential is going to change a bit more, and it is going to look like this. This is the potential due to anode. The anode is going to pull the electrons towards itself, right? But any of these has nothing to do with I mean, they have, but not really, I mean, great deal. So basic point is that you should understand this picture, that this is not the correct model. The electrons can come out, can leave the metal surface, and they will leave the metal surface if they are given an energy equal to phi, which is the work function of the material. And work function is a characteristic of a metal. It varies from one metal to another. Typical values for tungsten, for instance, the work function is around 4.5 electron volts, right? Tungsten is a very common material for electron guns for such experiments. So that is 4.5. For lithium, it is 2.3. For copper, it is 4.4. For aluminum, it is 4.25. So you see, it is in the range of 4 eV, 4 electron volts, right? So that is the range of phi. So phi is the work function, and phi is of the order of 4 electron volts. So now, with this setup, I've given you all the details. I've given you the motivation. I have told you what we have to derive. And now I will give you the steps, derivation steps. So the first point to note down is that for an electron to escape, the energy of that electron should, so E is the energy of the electron in the metal. If this energy exceeds EF plus phi, then the electron is gone. Then it is in vacuum, and once it is vacuum, it will be pulled by the anode very strongly, right? So this E should be greater than EF plus phi, right? Or in another words, you can say that E minus EF should be greater than phi. But I just now told you, but this fellow phi is of the order of 4 eV, right? If you transform eV into Kelvin units, which you can do, so you know that 1 milli electron volt is approximately 11-12 Kelvin, right? 25 MeV is room temperature, kBT, so you can calculate. So phi in units of kelvins is of the order of 40,000 kelvins. And what is the temperature at which the metal is emitting, throwing out electrons? 1000, maximum 1000, right? You operate your device in the temperature range from 600 to 1000 for controlling the current. This is to control the current. So your kBT, the temperature at which the thermionic emission is happening, is of the order of 1000 kelvins. So the point is that phi is much greater than kBT, even at temperatures where the metal is red hot and it's emitting out electrons, right? So phi is much greater than kBT. So therefore, now we can recast this condition. The condition for an electron to come out of the metal is that E minus EF should be greater than phi, and phi itself is much greater than kBT. So we can say that E minus EF must be much greater than kBT, isn't it? So therefore, we can say that E minus EF has to be greater than phi, and this has to be much greater than kBT, where T is the temperature at which the device is operating. Okay, or you can say that E minus EF divided by kBT should be much greater than 1, right? And if that is the case, then what will happen to the Fermi function, the Fermi distribution function that decides the occupancies of electrons in various states? So you know that the Fermi function f of E is given by 1 over exponential E minus EF by kBT plus 1, right? So if this quantity is much greater than 1, then exponential of it will also be very large compared to 1. We can drop this 1 out from the denominator, because 1 is very small compared to the first term in the denominator. Is this clear? Making sense to you? So if that is the case, then your Fermi distribution function for all practical purposes will look something like this: minus E plus EF by kBT. Right? I just took this term to the numerator by ignoring 1 from the denominator, and this is nothing but, you know, this will be a constant because EF is a constant. So it will be nothing but something like this: A naught exponential minus E by kBT. And this looks very familiar to you. This is the Maxwell-Boltzmann distribution. Right? At very high temperatures, the Fermi distribution reduces to this. Maybe you can. So what that means is that if you draw against energy the quantity dE, dE is the density of states. So the density of states goes as, for electron gas, the density of state goes as what? Square root of E. You remember that, right? Square root of E. It's constant in 2D and it goes as 1 by square root of E in 1D. So it goes like this. right. Now, if you multiply this with f of E, which is the Fermi distribution function, this product is actually what is meaningful, right. dE is just the skeleton. FE dE tells you how the states are filled, right. And you know at 0 temperature, all the states are filled till EF, and the states above EF are all empty. And that you can get from the 0 temperature definition of FE, which is 1 up to EF and 0 above it, isn't it? So, this quantity will become 0 for E greater than EF, and this quantity will become just dE itself for E less than EF, because FE is 1 for E less than EF, right? Right? You remember the shape of, right? So, the FE versus E looks like this. It's a step function at 0 temperature, and at a non-zero temperature there is a smearing, right, and this smearing is reflected here as well. So, at a non-zero temperature it goes like this. It has a tail, right. Now, if EF is here, you might have your phi here, right, and these are the electrons that will go away during the thermionic emission, the electrons in this tail region, because their energy is greater than EF plus phi, right. If the temperature is not high enough, then you might be somewhere here. So, if you are at temperature T1, which is much smaller, might be somewhere here, and then the chances of electrons coming out are very, very small, because your tail is hardly extending up to phi, right. It makes sense. Okay. So, if you want to find out, let me erase the pink or the pink plot. So, we did this in the last lecture also. If you want to find out the number of electrons under this curve, how would you do that? At any finite temperature, it will be from 0 to infinity integral FE dE dE. That will give you the total number of electrons, isn't it? So, the number of electrons is given by the integration of this area, right. So, this is your dN, the number of electrons in the energy width dE. This width is dE at some energy above EF, right. So, how will you write dE? dE is nothing, dN is nothing, dN is just FE dE dE, that is this area of this stripe. So, it is FE dE dE. Okay. Now, you can write dE dE, you can as well write this. You can as well write this as FE, and then for dE, for the density of states. So what is the definition of dE dE? What is this? What is this quantity? Number of electrons per unit volume in the energy range E plus dE to E, right. I can write this definition. In fact, this is what I did, this is how I derived the expression for dE in terms of Q points, right. So, this number is twice the number of Q points in the same energy belt, isn't it? Same energy belt, you just, because each Q point can take 2 electrons, right. So, this is same as 2 rho of Q d cube Q. So, you see what I have done is written this quantity in terms of the density of Q points. It's the same thing, density of Q points times 2 is the density of states. Okay. And how much is rho density of Q points? You know it now. You know it now. It's V by 8 pi cube. But since we are talking per unit volume, so it will be just 1 by 8 pi cube. And because there is a 2 here, it will be 1 by 4 pi cube, right? So 1 by 4 pi cube dq. So we can write this as A naught exponential minus E by kBt. That is coming from Fe, because Fe in this part has been reduced to this function, more like a MB function. And then you have your this quantity twice of rho q, that will be 1 by 4 pi cube. And then you can write for d cube q, you can write it as dqx, dqy, and dqz. Right, so you got the expression for dn, that is the number of electrons that can potentially come out when the metal is heated to sufficiently high temperatures. Okay. In fact, I should have. In fact, if I am really serious about these electrons to be out, to be emitted, this stripe should be above phi, isn't it so? Stripe should be above 5. So you can redraw it, or you can draw phi to be here, somewhere here. This is your phi. So these are the electrons. I had shaded this region, so actually it's this. I hope I'm not confusing you. It makes sense, right? Everything is clean and clear. Good. So now we are ready to find an expression for the current density, because we know the number of electrons that are coming out. So the current density is what? Current density is NeV. NeV. The electrons are coming out with a velocity v. N is the density, number density, and E is the charge, elementary charge on electrons, right? We derived this using Drewry's model. So therefore, the current density corresponding to this surface, right, the electrons are coming out. The current density, which I am going to write as djx, meaning along the x direction, should be equal to E with a negative sign, but I am dropping the negative sign here. Electron should have a negative charge, times Vx, they are coming out with a velocity Vx in the x direction, and their number dn. Right? So therefore, j of x would be just the integral of this quantity, and I can write v of x. I can write v of x in terms of q of x. So what will be the relation between wave vector and velocity? So this is momentum divided by mass, and momentum is nothing but h bar times the wave number divided by mass. Okay. So it will become E h bar by m times qx times dn, and dn is given over there, and we have to integrate it. That will give us jx with appropriate limits. So that is what now there are some details that I will discuss, but you have understood the point, how to calculate the current density along the x-axis. And this is the only current density that we are worried about. We are worried about the current along the x direction, because that is the direction along which the electrons are being pulled, right? And you can see also that the other areas are very small. Okay, so we are not concerned about what the electrons are doing in the y direction or in the z direction, right? Because the anode is pulling them along the x direction. So you just need to now plug in the numbers. So E h bar by m is going to come out, and for dn we will write that. So from there we get A naught out, and what else do we get out? And 1 by 4 pi cube out. So 4 pi cube, right? And then inside we have then qx, dqx, qy, dqy, like this. So we have integral integral E minus E by kT kBT times qx times dqx dqy and dqz. Now you can write E as h bar square by 2m times q square, which will be qx square plus qy square plus qz square. So you can plug that in over here, right? And then you can split this integral into 3 product integrals. Integration over qx, because this you are going to take exponential of this. So then you can write it as e to the power qx square times e to the power qy square times e to the power qz square modulo this factor in front, right? So if you do that, you will get 3 integrals and you integrate them and you will get the answer. Plug in E here. So exponential of x term plus y term plus z term, and you can write this as exponential of x term times exponential of y terms times exponential of z term, right? E to the power a plus b plus c is e to the power a into e to the power b into e to the power c. So your Jx would then be the current along the x direction, the current density along the x direction. Some prefactors which I am going to put in a box, which is for you to work out and worry about. Then you have an x integral where you have qx and then you have an exponential minus qx square kind of term with a with again, you know, some which I am going to draw with a circle. And this circle is what? This circle is h bar square by 2m divided by kBT. H bar square by 2m and kBT, right? So that is one integral you are going to get. The second integral you are going to get is even simpler. That has no qx, that is just, and of course this should be dqx. Second integral will be minus h bar square by 2m kBT times q y square, and then multiplied it by the third integral, which is minus the same constant q z square dqz, and this is dqy. Okay, so here this is this quantity, all right. So I am not going to write it, and this is nothing but h bar square by 2m kBT. Okay, now you can integrate this, but you have to fix the limits, limit of integration, right? So what should be the limit of integration? So let's first talk about the integration limit for the x integral. So for x integral, what should be qx min? Qx min, what should be qx min? Qx is the wave vector. You can think of it in terms of velocity. There has to be a certain minimum velocity, right? If the or energy, kinetic energy. So you know that, you know this condition, this is your condition. So your condition is that your energy of your electron has to be at least EF plus phi. If it is less than EF plus phi, there is no way, you are not going to see the thermionic emission, right? Now in this case, this entire energy is along the x-axis because we are talking about the emission along the x direction, right? So therefore this energy is what? Half m Vx square is equal to EF plus phi, right? So this is the, by the way, this is the minimum Vx. If the Vx is more than this, more than welcome. The electron will come out with some thermal energy, right. In fact, that is why you get a little negative, you need a little negative voltage to suppress the current fully, right. So, now you can write Vx in terms of Qx. So, you can write Vx as h bar square Qx square by m square, right. So, m and m will get cancelled out. So, therefore, the minimum value of Qx that you will get, Qx min, that would be, this 2 will go here. So, 2 times Ef plus phi, and then from here you will get h bar square, that will come in the denominator, right. And then you will get what else you will get? You have written this as h bar square q x square by m square. So, m and m got cancelled out. So, this m will come here, 2m. So, this is the value of Qx square. Then what should be minimum Qx? Square root of this, right. So, you can do that, and the value that you would get for Qx minimum is this. Because this was h bar square, when you will take the square root, only h bar will remain. So, this is your Qx minimum. And what should be Qx maximum? So, this we have fixed now, this quantity will be this over here. What is Qx maximum? What can be the maximum value of Qx? No limit, right? I mean, this entire tail is accessible. Sorry, I have erased it, but the tail can extend up to infinity. So, and along the y, so this is along the x axis. Along the y axis, you are not even concerned. So, it can vary from minus infinity, Qy can vary from minus infinity to plus infinity, and same for Qz. Okay. So, you have fixed the integration limits also. Okay. Now, with these limits, so here you have infinity, thankfully, in all the cases. Here you have some number which is given by this Qx min. This is also minus infinity. This is also minus infinity. Now, you see this integral. This integral is a standard integral, minus infinity to plus infinity, exponential minus alpha square d alpha, with a change of variable, right. You can put this whole thing as alpha, and then you can do that. So, there is a standard integral which is integral minus infinity to plus infinity e to the power minus alpha square d alpha, and this integral has a value which is square root of pi. So, therefore, the value of Iy and Iz, if I call this integral as Iy and Iz, then the values of Iy and Iz can be written down. So, then Ix we have not dealt with so far, but Iy and Iz are standard integrals. Iy is this integral. This is Iy. And similarly, this integral is Iz, and they are identical, and their values you will find to be root 2 pi m kbt divided by h bar. Now, what about the Ix integral? Ix integral is even simpler. You do not even have to resort to any standard integration. So, if this guy is alpha square, then 2 alpha qx dqx will be 2 alpha, right, is not it? I mean, this is an integral of this form, x exponential minus ax square dx. As simple as this, x exponential minus ax square dx, limit from some number to plus infinity, right. So, when you will integrate it, you take ax square to be some variable t, then you get 2x dx equal to dt. So it will reduce to an integral as simple as this, exponential minus t dt, right? And that will be just exponential minus t, and for the upper limit the contribution will be 0. So, you will get only the contribution from the lower limit, e to the power infinity minus infinity being 0. So, the I x will come out to be m kbt over h bar square times e to the power minus ef plus phi by kbt, and that quantity is a naught already. So, e to the power minus phi over kbt. Now, you are ready to plug in all the three integrals with this constant over here. So, when you will do that, you will find that jx actually comes out to be, after cancelling out the common terms, it will come out to be 4 pi m e kb square over h cube times t square exponential minus phi by kbt was already there, you just needed to, okay, and you can rewrite it. You can absorb this over here, multiplying it with a factor of, I think this should be pi cube, just check it, and multiply in the numerator and denominator by 2 and rearrange it. So, you will get this as, a t square exponential minus phi over kbt, which is what we wanted to derive. So, this is the relation, this is the Richardson-Dashman's equation, okay, and the constant independent of the material is 120 amperes per centimeter square per Kelvin squared. Okay. Now, of course, we are learning it here because it is of immense, it was of immense use, and it still is, because apparently what I was, before coming for this lecture, I was looking at some notes on Google, and I mean I came across something a bit weird, which says that the Apple phones that you're using and so on, so there the frequency range is very limited. You cannot access the whole frequency range, the frequency range which is applicable to humans. On the other hand, using these, the amplifiers and woofers and whatever, if they are made out of these vacuum tubes, you can actually access the whole range, and the sound quality is very, very different. But of course, you don't care about that, because you need very subtle ears in order to make a difference between a sound quality that you hear from Apple or from a device which really employs these electron tubes. And the other thing is that they are very bulky and they are very expensive. I mean, you imagine the size of a diode or a transistor that you use in current devices is very, very small. I mean, I think that diode that you use in the lab for doing IV characteristics must be 1/10 of the size of the nail, right? Even smaller than that. And look at the size of this tube. It's almost 2 inches long and almost 3/4 of an inch across in diameter. That's the diode that you would use. But I'm sure you might still be able to see or find some devices that work on this. Definitely in UG lab we have experiments where you use these tubes to actually, some of the experiments are related to this equation. That's why I thought I should derive it. Okay. So, in the lab what you do is you plot ln of j by t square. So, just last bit, yes, we have 2 minutes. So, in the lab you take a tube like this, you have a voltage source, you have a heating source, all these things are easily available. You can set up your experiment, you can put an ammeter here to measure the current So, then you are not measuring the current density, but you are measuring the current. You measure the current, you do not measure the current density, right. You measure the current, and from the heater voltage you will get the corresponding temperature, right. This is a little bit tricky part. So, basically the resistance has a certain temperature dependence that you would read in the advanced course, how you get it from the electron phonon interaction, right. So, it varies linearly with temperature for all practical purposes due to scattering against phonons. And that, so from the measurement of resistance of the heater, so you measure the resistance of the heater by measuring the current flowing through the heater and the voltage applied across the heater, you get the resistance of the heater, and the resistance of the heater is calibrated in units of Kelvin. So, if you know the resistance of your heater, you know the temperature of your heater, because the resistance of your heater is changing with temperature. As you are passing more and more current, the resistance is also changing. So, resistance gives you the temperature, and that temperature is the temperature of your cathode. So, you know the temperature now, and you also know the current, the anode current, because you have put an ammeter over here. So, that also you can put, and then what you can do is you can plot this ln I is the anode current, I by T square versus this minus phi over kBt. So, 1 by T basically, you can plot it against 1 by T, you get the T, and from the slope of this you can actually estimate the work function. You can plot it, you can make this plot, right. So, if you take ln of this by bringing T square here, you will get the relation, this relation should be a linear, should be a straight line, and from the slope you can get the work function of the matter. Okay. Is this clear? When I take ln, this side just reduces to phi. The slope will be phi by kb. That is it. So, we stop here.